All right, so we missed out a little bit on some Kirchhoff stuff, but I'll have to get back to it for in another way for the people who are not here. So we're talking about meters, and the basic unit we may remember from our pre-labs is a galvanometer, and that's what we see. I put it that the galvanometer, and that's was that big one there is a galvanometer. Usually galvanometers are centered and they go left and right. This other one here is uh, it's called it's written on it microamps, and there's nothing exposed here. It just shows the wires going into the meter. And you'll understand why I'm mentioning that in a minute. But basically, a galvanometer is made to measure very tiny currents. Very tiny currents. And the way that, and I guess because the people who invented these things, they didn't have power supplies, right? They had batteries made of some copper and some lead and some salty water and paper, blotter, voltaic pile, Volta, an Italian guy, and then Galvani, yup, he was using voltaic piles to, so that's exact piles of stacks of like you can do it with pennies and nickels, I guess, and salt water and blotter paper. You can make a battery. So they called them piles back then because they were piles of these things. And so, for example, Galvani took the voltaic pile and was taking freshly killed frog legs and was shocking them and making them switch. This inspired Mary Shelley, of course, to write Frankenstein, or at least use that concept in Frankenstein. So they needed to be able to measure very tiny currents because they didn't have very robust batteries. So you have this coil, and this is many, many turns of very fine wire, and then let's see if you can see it. Well, in fact, what they use, there's a spring here, I believe. Well, there is a spring. I'm looking for the connection wire, and I don't see them here. But there's these very fine wires here as well because you don't want them to restrict the movement of the needle. And then the spring, and then this little, no, not here. This thing here is this little lever that goes to this screw here, and that's just to adjust it to put it into the middle in this case, or to the far left for the case of what you see in the picture. And so when you pass current into this thing, I assume in this case we get a north pole going like this, and we're going to learn about that real soon. And then of course the norths repel each other and the needle will rotate to the right, and when some current is applied to it. Now the thing is, they usually the I max is usually on the order of microamps, 10 to the minus 6 amps. I mean, that big one here, this classroom one, it goes to 500 milliamps, so that's a lot of microamps, and that's just because it's so big. So it needs a certain amount of magnetic field. So the B field is a function of current. So there is a lower limit to how much current, because I'll get back to that in a minute. First of all, just galvanometers can only take a tiny amount of current. So this also implies that R of a galvanometer is quite small. So it's on the order of 1 ohm or less. So when you construct a meter, it's all about protecting the galvanometer. So when you make a meter, make a voltmeter or an ammeter, it's all about protect the galvanometer. So in the case of a voltmeter, and let's see here. So this one here is saying that it can take 5 microamps, or 5 times 10 to the minus 6. And let's say that I just measured this one over here. In fact, I got numbers here, so I'm going to change this. I was looking at this one here. That's 15 microamps. So let's just change that to 15 because I got an example I wrote out here. So let's say that we want at full deflection at 5 volts. So I want to meter that when I connect it to 5 volts, the needle comes all the way here to the right, and then I see it says 5 already, huh? So we also know that it's current through and voltage across. Now this is what engineers do, guys. You get a set of parameters and a set of parameters of the instruments you have, and then you have rules for what you're going to use the instrument for. So voltage across implies Vm is in parallel. So this implies that R of a voltmeter ideal is actually equal to infinity. So to satisfy these conditions as best we can, we take to make a voltmeter, we put a series resistor here. Let's see, R series, because we know when we add that, we'll increase the resistance of the voltmeter. I don't know what's up. Why my mouse cursor is flipping floppy. Must be something nearby. I got the stylus far away and it's still blipping around. So let's see. We know Ohm's law. And oh yeah, so I measured this ammeter here, and it's actually, I'm surprised that it's 5 ohms. I expected it to be a little less than that. So we're limited to 15 microamps. So remember that I total equals V over R total is always true. So in this case, our R total is going to equal, we want what, 5 volts, and we have a limit of 15 times 10 to the minus 6 amps. So 0.33333, I believe, 1/3, times 10 to the 6th ohms, which is also 330 kilo ohms. So we put a series resistor in there like that, and we can measure 5 volts with our galvanometer, and now we have a voltmeter. And unfortunately, though, we have to draw 15 microamps out of our circuit, so we have to sometimes worry that is 15 microamps too much. In fact, also in the real world, whoops, what is going on here? This thing is so jumpy. In the real world, it turns out most analog voltmeters have an R in. You know, basically, we can just ignore, right? In a series circuit with 5 ohms is like 330.005, so we can ignore the 5 ohms. But anyways, Rin for most real voltmeters is about 10K. And hint, hint, wink, wink. Remember in Tinkercad, I have one of the voltmeters with a 10K resistor in parallel with it. Also, Rin, another term for the input resistance of a device, is called the input impedance. Impedances. You're going to hear that word in your engineering careers and physics careers. A high input impedance means it's not much of a load, so it's a little counterintuitive. A low input impedance means that something will load down the circuit. So for measurement science, for a voltmeter, you want a high input impedance. Okay. Now, how does one make an ammeter? In fact, this is a homework problem in one chapter. So remember, current through, when we're measuring, so this means that an ammeter is in series. So that implies that R of an ammeter, ideal, is equal to 0 because we don't want a voltage drop. We don't want to add a voltage drop into our circuit. Or if we add another resistor, we're going to change a current. We're going to actually change the current that we're measuring. And once again, of course, I max, in this case, in our example, is 15 microamps. Just remember that depends on the movement. This is called the meter movement, just like a clock. In fact, a watchmakers were the original meter makers. And in our example, the R galvanometer is 5 ohms. So to achieve this, now remember, when you in series, and we're exploiting that, I didn't really say it, but in series, when I add resistors in series, I increase our total. So that's cool because we want the voltmeter to be high in resistance, and we want to limit the current in the galvanometer. So the series resistor is the thing to do, the key to that. In the case of when I want a low input resistance as well as a low current through the galvanometer, then the implication here is a parallel resistor or shunt. So we want to shunt away most of the current. So if we want 5 milliamps reading, full deflection, so that gives us I total equals I of the galvanometer plus I of the shunt. So 5 times 10 to the minus 3 equals 15 times 10 to the minus 6 plus, so it's very small current here. And in fact, I didn't finish this example, but if I have 5 ohms here and I have let's make the relationship here, 5 times 10 to the minus 3 divided by 15 times 10 to the minus 6. So that's 0.33 times 10 to the third. So we need a 1, 2, 3. So we need sort of a 300 to 1 ratio. So this guy here has to be 5 divided by 300. So that's quite a small resistance. In fact, if you look inside of these things, sometimes they have an actual copper bar so it doesn't get hot, because that's such a low resistance that I can burn it up. In the case of measuring 5 milliamps, that's not such a big deal. In fact, I don't have an example of these things in front of me. So this way, most of the current will pass through the shunt. And then in parallel, the smaller resistor, so R of the ammeter is basically, well, I even have to say approximately, is equal to R shunt. And my suspicion is that when I measured the 5 ohms here, what I was actually measuring was a shunt resistor. I just think that, no, let me think, no. It has to be quite small. But that implies the R galvanometer is much larger, and I don't believe it. So basically, your R ammeter is you want your R ammeter to be on the order of 1 to 5 ohms, or say 1 to 10 ohms. I think 10 ohms is too much. But it's definitely an exercise, before the advent of digital meters, definitely an exercise in material science to make resistors of such low value. And then just to finish up, so a digital meter, so we're so used to having them now. In fact, these digital meters that I play around with in front of you, this thing here costs maybe $10. Well, this is a pretty fancy one though. Maybe this one's 20. When I was your age, this would be $300 or $400. And of course, you can spend that much if you want a really accurate one. So let's think about this. So a digital voltmeter is what you do. What happens with a digital voltmeter? You have this circuitry here, and this comes in. This is an amplifier, and you put, when you connect something to it, it charges this capacitor. And the circuitry, it's kind of cool. The circuitry involves, anything that's digital has a clock signal. And just think of it as a square wave. And what's happening is, in the case of your voltmeter, it's opening and closing this switch. And it happens, like, if it's a megahertz, it's happening in every microsecond. It's opening and closing, so you don't notice it. But it's also why, if you look at digital meters, they sometimes take a little bit of a time to settle down. And so when the switch is closed, the cap charges. So S closed, the cap is charging. And then S open, cap discharge. And the amplifier just increases the output. And it also means that, remember, R of a capacitor equals infinity. And we want the ideal voltmeter also equals infinity. But what the amp does, makes the input impedance about 10 megohms. And all it does is the circuit after this measures the t to the 1/2. Remember this? The half-life, or the 1 over e life, a time constant. So the circuitry here just measures the decay rate, and it can figure out what it knows: the input resistance, it knows the input capacitance, and by measuring decay rates, and well, we got to think about that because it's independent of voltage. Now, I guess the cap, maybe it's the cap. Ah, I know why. The cap doesn't get charged completely. That's how it works. Yeah. So then you can figure out what, right. So the cap never charges completely. So it starts at a certain point, and I don't remember the details, but you can imagine, you can hand wave your way around it. That it's by charging and discharging the cap, but not letting the cap max out, that they can figure out what the voltage is. And you can do this the same with the how do they do a current meter? I know that, that's a good question. I don't remember. But a digital ammeter, the other thing with a digital ammeter, there's little difference between digital and analog, little difference to a digital and analog ammeter, it turns out, because it's trying to achieve R equal to 0, of course, is just not possible. Okay, so I'm going to actually stop this recording and start a new one.